You know those wires? The ones crisscrossing the sky pretty much everywhere you look? Yeah, they're such a normal part of the scenery that we barely even notice them anymore. But what if I told you that behind every single one of those wires is an entire set of invisible rules, a hidden code that keeps our world powered up and, safe? Today, we're going to pull back that curtain and take a peek inside. No, seriously, just think about it for a second. Let's say you're hanging some lights in the backyard for a party. How far can you actually stretch them before they start to sag dangerously? Or what about that big power line that feeds your whole house? What's stopping that thing from just snapping in a bad storm? You might think it's all just common sense, but it's not. It's actually a science, and it's all governed by a very specific rulebook. And that rulebook, it's the master document for pretty much any electrical setup you can imagine. We're talking everything from the wiring inside your walls to the lights strung up over a city street. It's called the Electrical Safety Code, and we're about to dive right in. Okay, so its official name is the National Electrical Code, or just NEC for short, and its mission is totally crystal clear: the practical safeguarding of persons and property. See, this isn't just about making things work. It's about preventing fires, electrocutions, and all the other scary stuff that can happen when you mess with electricity. It's a huge reason our modern world is as safe as it is. So let's get down to the nitty-gritty. We're going to look at one small but really crucial part of the code: the rules for overhead wires. This gets right to the heart of those questions we started with. How far can a wire actually go, and what does it need to be made of to be safe? Before we get into any specific numbers, the basic idea here is just simple physics. Think about it. The longer a wire is, the more it weighs, and the more tension it's under. It's just like a long clothesline sags more in the middle than a short one, right? Plus, a longer wire means electricity has to travel farther, which creates more resistance and more heat. So the solution is pretty logical. For longer distances, you need a thicker, stronger wire. All right, now to understand the code, we have to talk about wire size, which is measured in something called American Wire Gauge, or AWG. And here is the one tricky part you just have to remember. The system is kind of backwards. A smaller number means a bigger, thicker wire. So an 8 AWG wire is actually thicker and stronger than a 10 AWG wire. Just keep that little tidbit in your head. So, check this out. Here's how the NEC puts that physics into actual practice. This table shows us that the magic number is 50 feet. For any span that's up to 50 feet, you'll need at least a 10-gauge copper wire or a thicker 8-gauge aluminum one. But the moment you go over 50 feet, you have to level up to an 8-gauge copper or a really beefy 6-gauge aluminum. It's that physics principle, just written down as law. Okay, so that covers the big utility lines. But what about something a little more fun? The code actually has specific rules for festoon lighting, which is just the official fancy term for the string lights you'd see on a patio, in a beer garden, or at an outdoor wedding. So, you've got this string of awesome-looking lights. You want to hang them between two trees in your yard. How far apart can those trees be before you're actually breaking the code and, more importantly, creating a hazard? What do you think? 20 feet? 50? Maybe 100? And the answer, according to the NEC, is 40 feet. That's about 12 meters. That is the absolute maximum unsupported distance. If you go even 1 inch over that, you got to bring in some extra hardware to make it safe. So, what do you do for those longer spans? The code is super specific. First, you have to support the electrical wire with something called a messenger wire. This is basically a strong steel cable that takes all the tension, so the electrical wire itself is just kind of hanging along for the ride. Second, that strong messenger wire has to be connected at both ends using strain insulators. You've probably seen these. They're usually those ceramic or glass knobs that don't conduct electricity. They stop any stray current from dangerously electrifying whatever you've attached the wire to, like a pole or a tree. The code also gets really specific with a safety checklist. You have to use a wire that's at least 12 AWG or thicker. And then we get to the really critical don'ts. You can never, ever attach these wires to a fire escape, a rain downspout, or any kind of plumbing. And why is that? Well, because those are all metal systems that are supposed to be completely separate from the electrical grid. If a wire's shorted out on one, you could energize an entire fire escape or all the pipes in a house, creating this incredibly dangerous invisible hazard. You know, it can be easy to get lost in all the numbers. 10 gauge this, 40 feet that. But it's so important to zoom back out and remember why all this stuff exists in the first place. It really is about so much more than just a wire. So here's the bottom line. Each rule is there to stop a specific danger.
Using the right thickness of wire, like we talked about, keeps it from overheating and starting a fire, or from sagging down at a traffic. The messenger wire makes sure the whole thing doesn't come crashing down in a windstorm. And those rules about where you can attach it, they're there to prevent deadly electric shocks. It's like a three-part system for safety.
So, let's sum it all up. The big things to remember are longer spans always need thicker wires. For those party lights, that 40-foot rule is your golden rule. And please, please never attach an electrical wire to your plumbing or a fire escape. All of these rules from the National Electrical Code are working together, silently, in the background, to create this hidden layer of safety that protects us every single day.
It really makes you think, doesn't it? The rules for the wires overhead are really just the beginning. Our whole world, from the foundations of our buildings to the design of our staircases, is shaped by codes just like this one. Now that you've seen one up close, you might just start noticing the evidence of others all around you. Thanks for digging into this with me.